think it's recorded. Oh yeah. Yes, this time I did. Um, yeah, so for this time, last time it was just forces of flight, lifts, and lift generation. This time, what we're gonna go into is how drag and lift are correlated, what drag is, the aspect ratio, more about that, wing geometries, Reynolds numbers and why that's important, and then just lift and drag ratio. Somewhere. Oh, okay. So last time Rainier isn't here. Rainier asked a good question, and that was about the lift equation, if it's a 2D equation, if it's a 3D, and I told him it was a 2D. I was wrong about the lift equation depending on the CL. The CL is a unitless number, so you can use it for either 2D airfoils or a 3D plane. You can use it for the whole wing area. Just something I want to point out. I was wrong one, but sorry. Um, so I'm gonna answer this later, but just like have it in mind for now. When golfers, they hit the golf ball will go so much more farther than just a regular size ball without the dimples. So why do you think that is? I'm gonna answer that later. Just like think about it for now. Okay, so last time we talked about parasitic drag, and there's three types. This time we'll be talking about induced drag, which is the other type of drag. Whenever you're calculating for total drag, you just add parasitic to induced drag. But induced drag is a drag that's caused by airplanes generating lift. So when an airplane is flying through an area, it's taking off, whatever, it's displacing a certain amount of air. And that air that it's displacing also generates lift. It starts building up, and at the edges of the wing, you'll see it most. So what happens is that these vortices are generated, and you can see what a vortice is like here. It's these big cones of air that are forming at the tips of the airplanes that are like pulling it back. And here's the equation for drag force. CD is very similar to coefficient, it's just drag coefficient. It's also unitless and it's also found experimentally. You have to find that value experimentally, just like coefficient of lift. A is the reference area, so it can be the whole wingspan, it can be two-dimensional part. P or rho is the density of the fluid. V is the flow velocity related to the object, such and so forth. So what happens is that on really what you want is for this to be straight drag component. It's no longer being directly up. That's just building up. That's important. The vortices are formed from the downwash, so all that displaced air from the wing itself building. Here I have video of it. Show you guys. It's like a short. No, it's a 6 minutes, not the pulses. Okay, here you see it. The vortices as it actually goes through the right through the both sides, whatever. But yeah, you see these vortices just forming. Why is it not? These vortices just forming here, so they can get as it flies through cloud, you'll be able to see it. We can show this with a wind. But you see these big vortices forming. For pilots, this is called wake turbulence. So the reason why we have different types of airports, if you go like down the Kendall, you'll find Miami Airport, and you have Miami Executive for civil aviation for smaller planes like Cessnas, Pipers, so on and so forth. And then you have Miami International, which is for the huge like 777 Dreamliners and such. A small Cessna can't take off immediately after a Boeing Dreamliner just took off because it will have such high wake turbulence that if the little Cessna were to take off, it'd get ripped out of the air from all of this turbulence that's like here. Yeah, aspect ratio. So Josh asked about aspect ratio last time. It's the relationship between how long the wingspan is and how like thick it is as well, like the chord length from the leading edge all the way to the trailing edge. Um, Aspect ratio is important because it shows us the relationship between lifts and how efficient a plane is at generating lift. So a glider, for example, like the little plane I showed earlier, they have this huge and long wingspan, but oh, have like a huge, oh, just like for his, oh, just disappeared. Whatever. Um, so gliders have this huge long wingspan, but they have a short chord length. So as it starts flying, gliders are very efficient at generating lift and they can stay up in the air for a long amount of time, but they can only go at slow speeds because they're almost entirely made out of composites. And because they have such a long wingspan, they can't go at higher speeds because they're structurally not going to handle that. They'll actually just break. Um, so gliders have an aspect ratio of anywhere from 30 to 20. A Cessna would have an aspect ratio of 7 to 7.4. And fighter jets like the F-15 that I showed earlier has an aspect ratio of 3 to 4. Planes don't have like one fixed aspect ratio because especially like with modern planes like the 777 Dreamliner or the A330, the leading edge has a slat. So the airfoil itself will actually extend outwards and become bigger to generate more lift. We'll have a bigger camber. Um, yeah, okay. So when it comes to a glider, gliders have a long wingspan, but they don't have a lot of mobility. They're not stable. They're not statically stable. So when it comes to them actually having to turn, the glider wants to return to an equilibrium state. It wants to return to like just a fixed regular state that is stuck. So, for example, because they have such a long wingspan, they find it more difficult to move. Opposed, if you have a fighter jet, you can see fighter jets easily like turn around and go in the opposite direction, even though they have a lower aspect. Yeah, nice. No, no, why did I say fighter jets are safe? Could have misspoke. Probably misspoke. I probably misspoke. But want a shorter wing because you have all imagine that with a larger wingspan you're generating more lift, right? But you're also generating more drag that's pulling you back, trying to get you to an equilibrium. Like fighter jets, they have those small canards up front, and they have a really thin and small wing. Yeah, those would also change a lot. That affects downwash. I'm not exactly sure how. I'll answer that next time. Right. Yes. The flying wing itself, the good thing about the B2 and all flying wings in general is that when you have a regular plane taking off, you have a fuselage, and that fuselage is displacing a lot of air, right? It's not aerodynamic, it's just drag. Suppose with the B2 or any flying wing, the whole fuselage is an aerodynamic surface. It's a airfoil. So yeah, it is. Those work more like gliders. It's the one that doesn't have landing gear. But it's the one that yeah, It is. What did you say it was? I had to stop writing. Okay, so this is the lift to drag relationship. Tomorrow, when we use XFLR 5, I'll go into more depth about it. Also show you guys obviously how to use XFLR 5. XFLR 5 is a great tool that helps us graph everything. I showed Bravo that today. It can show you the downwash a plane produces. It can show you the lift and where it produces the lift. Airfoil. You can make your whole plane on XFLR 5 and have it simulated. It's a really good tool. I'll show you guys how to use it tomorrow. But the lift to drag ratio shows the efficiency in generating lift, like an airfoil or a plane. Planes with a higher lift to drag ratio are usually like gliders and airliners, and shorter lift to drag ratios are like fighter jets and more militaries. And acrobatic planes as well, because they also like the Red Bull planes that you see like flying, Blue Angels, right? That's just it. You can see CL and CD curves here. The CLCD, it I put on exit 35. I'm not sure what this was grabbing. The parasitic drag, the top average, the parabola, that's where parasitic drag is equal to. Um, yeah, and planes with, yeah, I went over most of that. Yeah, yeah. Eh, so let's remember like move back to what aspect ratio was describing. When we have a lower lift to drag ratio, they're more unstable. So what that means is that they'll have more thrust to accommodate that. More unstable, but they'll be more maneuverable. Unstable meaning that they don't return to a fixed. Not exactly. I mean, that would depend as well on the thrust. Yeah, or a glider. It would continue going at that. It would have what do you call it? I started talked about it on the first day. I forgot it. It's like for every it goes down, it goes. Yeah, glide ratio. That's yeah, that's what. Yeah, not sure. I exactly have it too. Yeah. But, generally want a higher lift to drag ratio because God forbid it happens. We are responsible for it. I just made that very clear. Um, I'll show you guys that tomorrow. That software just was explain. We want stability, yeah. But we also want it to be maneuverable. So we don't want the wings to be too large. So they're causing too much drag for us. Not be able to. The good thing about our UAV that's unlike a glider is that we actually have thrust. We have forward motion. And we have rudders, working like strong rudders that will help us. Probably not though. That could be the spring project one. Yeah, just yeah, just regular straight. Canards are kind of like the things up front. Yeah, you don't see that on typical. That's the whole other thing. Yeah, yeah. They stall before the rest. Really good for somewhere in between, somewhere like a Cessna. It's not like really nothing. Okay. Yeah, so Reynolds number is basically what shows us how lift is. Like, okay, the official term is the lift regime, but that's no, I'm sorry, I'm speaking of the flow regime. So it's basically showing us if flow is going to be laminar and smooth. Generally, when we're flying, we want laminar flow, but obviously, the higher and higher you get turbulent flow, depending on whatever environment you're in. Let's say you're in storm, turbulent flow. Um, okay, so yeah, Reynolds number predicts how airflow will be given in a fluid density, fluid speed, characteristic length, which is the core length, leading edge to the trailing edge, and fluid viscosity. So what viscosity is just like the fluids that you're in. It's kind of like the resistance to like water, obviously, is high viscosity than air. Yeah. So it's all the same equation. Internal force, which is just the force that's experienced versus the viscous force, like the resistance to motion. So this whole part, I'm not going to get that much into. But if you look at the Reynolds number, because it's just the derivation of it, and kind of like want to go faster with time. But at the end, you get the fluid density times the chord length of the plane, times the velocity that's in, the velocity of whatever it's traveling in, or if you're testing in a wind tunnel, the velocity of the same, divided by the viscous force, like the resistance to move. I've written them all of the equations. Oh yeah. Thank you. So up here with lower Reynolds numbers, you have more smoother and laminar flow. Obviously, for different purposes, you'll have different types of laminar flow. So even for this instance, we have smooth and laminar flow for a ball at 5 Reynolds numbers. Anything less than 5 Reynolds numbers is smooth and laminar flow. But as you begin to increase, the flow becomes more and more turbulent, right? And eventually it just becomes completely turbulent at Reynolds numbers that are for 300,000. This isn't to say that for all cases it's like this. For example, for a commercial plane, you'll have Reynolds numbers in the hundreds or thousands, right? That for smooth and laminar flow. So it's just a range. It's just showing you like the different types of flow that you can have. This isn't a universal thing for all. Yeah, it'd be the distance from the leading edge to the trailing edge. Someone has a question. Yeah, it's being recorded. Oh, what else I should say? Oh, wait, you said something. Oh, okay. Have a good day. What was I so? So you can different depending on what subscale we can simulate a large plane in a small area, in a small wind. So most wind tunnels like the one here at FIU are a foot by a foot long, like the testing span. But let's say we want to test a 777 Dreamliner, which has Reynolds numbers in the millions, right? if we reduce the amount of Reynolds numbers and we keep it constant, like all of these things, reduce it, accordingly for it to fit within the one by one testing chamber, you could simulate huge Dreamliner from a wind tunnel without ever having to actually build it in a smaller testing, have it give you the same data. So obviously that's why we have subscales, right? The smaller and smaller planes we have will have Reynolds numbers and no more than like 200. And eventually at the end of it, I want it to be somewhere in the range of 200 to 500. That answer, yeah, 100. Yeah, and we can show you. I'll show you that tomorrow. Exit five. Actually, let me write that down. Oh, this is being just okay. So, does anyone have an answer for the golf ball thing? Like why a golf ball travels fast? Are there? And just I don't know. You know? I took golf. Yes. So what happens is that on airfoil, like just a regular ball, for example, we have air passing over it. But for lift to be generated, you need air passing over the whole area. You can't just have it separating at one point. So what happens is that by having dimples in the golf ball, it creates turbulence so that air will be passing over the top surface of the golf ball and generating lift. And then we see this as well on planes, where obviously when you're taking off in turbulent conditions, or if you're going through a cloud, while piloting clouds, um, there's these parts of the plane that will generate turbulence such that there's still air passing over the whole section. I just think it's something interesting. And then the Kahoot, okay. Yeah. On a plane, like for the wing, you wouldn't. There is, but it's not like, see, for example, like on a wing, for example, here we can have these little sections which induce it for the wing. But I know what you're talking about, right? It's like that kind of like shark's fin. Yes, that's way too complicated. We can't, I mean, there's people trying to make that material more accessible. It's just that imagine if you had basically what Angel's talking about is having the whole area of a plane, having these small, like, basically like these, right? But on a microscopic level. There's people who want to do that so you induce like a small amount of turbulence to keep more air flowing on and thus generate more lift. The issue with that is that it's very sensitive. So it would break easily, breaks easily. Now, it's just expensive to have it on the whole. That's like the issue. Add to it. So Reynolds numbers, I want it to be somewhere in the range of like 200 to 500, just so that you know. Obviously, when we do simulate the UAV, I want to simulate it in turbulent conditions. So that's like expect the worst. What's the rest of it? Lift to drag. I mean, a lift to drag depends ultimately on what we want the UAV to do. If it's for the weather projects, then it depends on how much all of that. But I would say a rough estimate, generating 33 joules. And drag, I'm not sure. Drag, we'll see. How much drag it generates. Yeah, drag and lift are both well, what issue is that they're all broken. Yeah, the compressor is that they're all old, painfully old, right? So the compressor in them, the part that actually makes the air pass, broken, and none of them are being used except the supersonic one. Yeah, and we can't. Um, in the past, we could ask Boots, and they'd be like, "Oh, could you talk to your UM people and see if we can use the wind tunnel over there?" But he's a UM now, so awful. I want to see if we can fix if FIU's ever going to fix the subsonic wind tunnel. Then, because I'd rather use a professional wind tunnel than our wind tunnel at home. XFLR5, yeah. I mean, last year they were pretty close. I mean, it's less about because it depends on what you're exactly plotting on XFLR. So the reason why SolidWorks simulations will also be because you're maybe not choosing the right material. There's like something a little bit off that leads to a big issue later on. It's more about what you're inputting into. So it's really depends on what you're, but it's usually pretty accurate. And even when calculating like CG and everything, we'll see. Hopefully. Yeah, Kahoot. Um, is everyone in the Kahoot? So yeah. So induced drag is the air, it's all that displaced air that's pulling the plane back, pulling the wings back. So that's what induced drag is. Friction between air and the wing surface is another type of drag. It's a type of parasitic drag. It's the friction between the air itself and whatever material you decide to build it. That's a type of, yeah, just like build up. Yeah, builds up across the wing. Yes. So that's where you get those vortices at the very tips of it. Also, I have the equations on the side. just so like yeah, so this was just like a rough estimate. A glider, remember, has a very long wingspan, but very thin like chord length. So what happens is you look at formula, it's chord length squared divided by the area of the total length, like from a top. Oh, okay. Oh, okay. Let's skip it then. Yeah, and that goes back to like you'll see it tomorrow next to the graph them both at apogee. Parasitic drag is equal to induced strike. You get the most of both. Oh, you all got it. That's okay. Yeah, so Reynolds numbers, I've written it down here. It's the air density times like the chord length of what you're testing, times the velocity divided by fluid viscosity. Let's wrote your name on this. I know who the one is. You don't have to say it now, but I know who you are. Just saying. Figured it out. It's fine. Get the drag equation right here, buddy. We just like multiply. If we take just the drag equation, then we can Oh, okay. Well, if you take the drag equation that you have here, just like yeah, yeah, yeah. Will always be 1.2 98 rooms. Rho is density. Oh, this one I forgot to change the time. That's all. That was a time constriction. I'm just gonna assume you guys guessed on that one. It's fine. You're a victim. Or no, you're a victim. I'm not gonna throw this because last time I threw it. Um, but that's it for the Kahoot. I'll add all the questions that were asked here, so that way when I send it again in the group chat, you guys can have it. Just to see. And then at the very end, I included all these videos. I don't go into a lot of depth in this. If you guys watch these videos, they'll go into a lot more depth about every topic that I discuss. And then if anyone has time, you'll find like the free PDF online. I put like what chapters this correlates to framework there in the bottom. Yeah, that's pretty much it. Thank you guys.